Welcome to Tuesday. So, yes, busy week, busy week. I will not be here, but I guess when I'm announcing Friday's a B day, I should also say I will be here Friday. This is the conference tournament for bowling. And since I coach the Bentonville West bowling teams, I will not be here. I'll be out all day with that tournament. And that'll affect some next week's schedule too, but more on A day next week. So, all right, let me see if I can't get our lesson up on the screen. Get us started. We got a bit to cover today. Yeah, we got a bit to cover. Let's get this up here. Okay, let's see. What is today? Fifth hour. Fifth hour. We're in fifth hour now. So okay, let's go to our grade screen as usual to see where we are at. We've already done the first three. So those are already past due now. So got those turned in. Today we're going to learn about graphing exponential functions. All right, thank you, Aaron. And graphing logarithmic functions. So today we are learning to graph functions. We've learned exponential functions 2 weeks ago. We learned logarithmic functions last week, and now we're going to learn about graphing both of those. So lessons 5.05, 5.06. You've probably never heard of the Sierpinski triangle. Sierpinski was a Polish mathematician during World War I, so over 100 years ago, because that was the 1900s, around 1917 to 1920 era. And he worked with fractals. A fractal is when you take a geometric figure and you divide it into pieces that are the same shape as the original, but just smaller. So you take a square and you divide it up into 4 squares that are all like the original square, just smaller. And then you can take those 4 squares and divide them into this one. So this is known as the Sierpinski triangle. So let me pull this up here. The audio. All right, just a minute and 8 seconds. This is a pretty cool description of how you derive the Sierpinski triangle.
One method of creating the triangle is by first drawing an equilateral triangle. Remove another, smaller equilateral triangle from inside the original. The vertices of the removed triangle meet at the midpoints of each segment of the larger triangle. Next, 3 more equilateral triangles are removed from inside each of the remaining 3 triangles. The process of removing triangles inscribed within the larger triangle can continue forever.
All right, they get smaller and smaller and smaller, but that is the Sierpinski triangle, which is known in mathematics as a thing, because fractals is there's some professors. I had some professors at the U of A even that really spend their whole career studying fractals and what we can learn mathematically from a fractal. So that is the Sierpinski triangle. And you wonder, what does that have to do with graphing exponential functions? Well, actually, Sierpinski's triangle demonstrates an application of an exponential function. So an exponential function, if you remember, is where the variable, like the x, is the exponent. It is located as the exponent, and then the base number can't be 1. If it's 1, you don't have an exponential equation because 1 raised to any power is just 1. So that's actually just linear. But the exponential function being used in Sierpinski's triangle is f of x equals 3 to the power of x, where x is the stage at which the triangle is removed. Like you start at stage 0 when there's no triangles removed. And after the first stage, you've removed the triangle from the middle. Then at the second stage, you've removed the triangle from the middle of all those triangles. So let's look at how that equation relates to Sierpinski's triangle here. So we got another short video here explaining that. And yes, I know sometimes these videos move way too slow with their graphics, but it is what it is. So here we go.
The exponential function is f of x equals 3 to the x. At stage 0, when x equals 0, the function equals 1. indicating there is only one solid triangle. This is how the fractal begins. At stage 1, f of x has a value of 3. This means that the first time a triangle is removed from the center, there are 3 triangles left. At the second stage, f of x has a value of 9. So 9 triangles remain. At stage 3, f of x has a value of 27. So the third time equilateral triangles are removed, 27 triangles are left, and so on.
All right, so you can see how that actually does illustrate this exponential equation 3 to the x power, and that's related to Sierpinski's triangle. So it says if you graph the exponential function in Sierpinski's triangle, so the domain is all real numbers, but what is the range, right? Which is the group of numbers that can be produced from all the domain. So if you look at the graph, it appears as if the y-coordinate is 0 when x is less than -3, but algebra tells us something different. Let's take a look here. If x is less than -3, like -5, well, if you substitute -5 in to that equation, 3 to the -5th power, you have to rewrite that as a positive exponent, so you move it underneath the fraction. You put a 1 over it. 1 over 3 to the 5th. 3 to the 5th is 243. So it's actually 1 243rd. Very, very, very small number. If it's -4, 181st. It's -3, 127th. -2, 1/9. So it just gets really, really close to 0 the more negative x gets. It just doesn't ever get there. So it's basically approaching an asymptote at 0. An asymptote. So let's take a look at this right here. If we have a base between 0 and 1 or a base greater than 1. So in an equation, let's look at a base greater than 1. So the base is the number that is being raised to the x power, right? So this is at 1.5. If it's a base 1.5 raised to the x power, it looks something like this, right? This is an asymptote at y equals 0, so it's getting closer and closer. The more x goes negative, the closer it gets to 0. It just never touches it. Now on the right end, it goes all the way up to infinity. Now let's look what happens when the base gets larger than 1.5. Let's see what changes. 2, 2.5, 3, 3.5, 4, 4.5, 5. See, it's just getting steeper. It's getting closer to infinity faster. It doesn't really affect the left side. That's still approaching 0. So the base being larger than 1 just affects the steepness. The larger the base, the more steep the graph. So let's look at the other situation. Base between 0 and 1. All right, so between 0 and 1. So like if it's 0, look, if the base is just 0, 0 raised to the power of anything is just 0, but only on the positive side. Notice we can't have negative side because if you have a negative exponent, you have to move it under the fraction, and you can't divide by 0. So it only exists there. But let's move it up. 0.1. 0.1 raised to the power of x. You could also call this 1/10. 1/10 raised to the power of x. Anything between 0 and 1. Now let's look at this. As this gets closer to 1, it gets less steep. 1/2, 0.6, 0.7, 0.8, 0.9. And if it's 1, it's just a linear equation now. 1 raised to the power of x. That'd be 1 squared, 1 to the 4th, 1 to the 8th, 1 to the 10th. It's all equals 1. It's just linear. 1 raised to any power is just 1. So that's why that's just linear. So between 0 and 1, it's an exponential equation. And the closer it is to 1, the flatter it is. The closer it is to 0, the steeper it is. So this is closer to 0 is steeper when it's a fraction. And if it's greater than 1, then it's steeper the larger the base. So a little bit different there. So we can see if we do a base of 2 and a base of 1/2, those are actually a reflection of each other. Those are opposite. They have the same graph, just reversed, mirrored over the y-axis. All right. So it says move the slider on B when the base of the exponential is greater than 1. Describe the graph. Well, when it's greater than 1, it's steeper the larger the base. That's how we describe the graph. Check the answer. From left to right, as the x-coordinates increase, the y-coordinates also increase. As the base increases, the slope of the graph becomes steeper. That's what we said. And on the left side, it always approaches the horizontal asymptote of y equals 0. So it's got more questions there. Basically the same thing we just looked at. Greater than 1, once you go through those. We did that. What about when the base is 1? It's a linear equation then. It's just f of x equals 1. If it's 0, we talked about that as well. So, all right, let's go to page 2. We got nine pages on this. A lot of them are practice problems. They're not all 9 pages of lesson. Okay. This is a good reminder. This video is going to remind us how exponential equations work and what those bases mean, because we need to understand what's happening, and that'll help us understand graphing. If we know by looking at the equation what's happening, it's easier to know if our graph is correct. So we're going to watch this video real quick where he explains 3 different examples of how exponential equations work.
Today I'm going to show you how to use the properties of exponents to interpret exponential functions. In this particular set of examples, I'm going to be referring to the value of boats. I have boat 1, 2, and 3. So beginning with boat 1, the very first number you're going to see is 5,000. This is the initial value of the boat. The next thing you're going to notice is being multiplied by 1.25. This is our percent of change. What is happening to that initial value? And then our exponent of x is where we would put our numbers of years. So if I wanted to know how much his boat would be worth in 10 years, I would replace his x with 10 and then evaluate this. So what else can I tell about boat 1? Well, we know, like we said, the initial value was 5,000, but it's being multiplied by 1.25. What does that tell us in terms of percentage? The number is greater than 1, so it is keeping its value, but it is gaining 25% in value. So if I were to classify this, I would say that it is increasing. So boat number 1 actually is increasing its value year after year by 25%. Now looking at boat 2, same thing. Notice we have the initial value first. It is a value of $4,000. Here our percent is 0.40, our percent of change, and we have the x for our number of years. Now the difference between these two, you'll see, is that this one is greater than 1 and boat 2 is less than 1. So what does that mean? It means that we're going to keep 40% of our initial value. So we know our percentages go up to 100. So if I keep 40, that's also saying that I lost 60. So if I'm classifying this one, I would say it's decreasing. I'm actually losing 60% of the value because I'm keeping 40%. So when I'm looking at boat 3, I have it just in words, but not in the expression. So how can we make that happen? Here we have an initial value of 4,500, the same as we have with boats 1 and 2 at our initial value. Then we're multiplying by our percent of change. So here it says it's losing 50% each year. So if we are losing 50%, that means we are keeping 50%, expressed as 0.50. And then the last thing we add is our x, which is our number of years. So we can easily determine by the way it is written here, our percent of change is less than 1, so we know it's decreasing. And of course, our problem actually says it loses. So we would say it is decreasing. Now, when you look at these two, we have 4,000 times 0.40 and 4,500 times 0.50. A lot of times we tend to think, oh, well, this is decreasing by a lot less because it is 0.40. But really, notice we are keeping 40%, meaning that we are losing 60%, as opposed to here, we are losing 50%. So if you were comparing these two boats, this one is losing value at a much faster rate than boat number 3. So knowing what these numbers mean and knowing how to classify them as increasing and decreasing be very helpful in interpreting these functions. And that is how you use the properties of exponents to interpret exponential functions.
There we go. So we need to know that when we're dealing with these exponential functions. It's helpful to know whether something is going up and increasing or whether something's going down and decreasing. Because when we go to graph these, our graph is either going to be increasing or decreasing, and we should have some idea is that correct? Should it be increasing or decreasing? All right. So now we're gonna put some notes up here. Let's take our notes for today to figure out. We need our notes because with quizzes and tests coming up, and we need to have notes that we can use. That maybe you can always use all your notes on any quiz or test that we have. So let's look at the key features. The key features. Now, the key features of exponential graphs, it's just like any other graphs. We always want to know what the y-intercept is and what is the end behavior. So we're going to take some notes here. There we go. Let's get the sheet up here on the page. So if we're looking at an exponential equation, and remember with an exponential equation, it would be something like, I'm going to put f of x equals p, and we use p as like the starting amount, like the principal if it was in a bank, times b, the base, raised to the power of x, base to the, and then we're going to put a plus k on here because that can affect things. We can have translations of equations just like we do with anything else. In fact, let's look at that before we get too far in our notes. Let's go to Desmos and talk about translations of exponential equations. It works just like translations of quadratic equations and linear equations, and when we did to the third power and fourth power, and all those, it all works the same. Let's start with a basic equation here, and let's say it is, well, let's just do a 3 to the x, the very most basic. Okay, 3 to the x. We see it crosses the y-axis at 1, so that's our y-intercept, 0, 1. And it approaches the asymptote to the left as it goes into negative infinity, gets closer and closer to 0, and to the right it goes up to infinity. So what happens if we put a number in front of that? Let's put this, let's put that in parentheses. Because if we had a p, because we have pbx, right? So let's say we start with 10. What did it do to our equation? Well, it made it go up faster. It moved our y-intercept to 10. Interesting. What if this number is not 10, it's 5? Oh, look, our y-intercept is now 5. Whatever that p number is, like I say, whatever the p is, because we're just doing like 5 times 3 to the x. There is no plus k. It's just 0 right now. Plus k is 0. Our y-intercept is ending up to be whatever that number is when we just have a base raised to the x power. Let's make this -2. Let's see if something happens there. Oh, look, -2. It changed everything. Now the graph is going down. But that is our y-intercept. -2. -4. Oh, yeah, that's our y-intercept. Let's go back to the positive side. 4. 4 is our y. So we can find our y-intercept when we have a base exponential equation like this. Now we're talking about that plus k. If we put plus k, and it says, okay, do we want a slider for k? Okay, if k equals 0, k equals 0, so it's plus 0. Not much has changed. I mean, it's still exactly the same because we added 0. But what if we add 1? Make k 1. Oh, quite a bit has changed. Let's take out the slider and just put plus 1. We're just going to put plus 1. Let me put the original equation back on there without the plus 1. times 3 to the x. See, the green one is the original. The new one is the red one when we put the plus 1 on it. So what happened with the plus 1? Well, the y-intercept that used to be, here goes the green, it used to be at 4, has now moved to 5. It went plus 1. But if we also look at the asymptote is no longer y equals 0. It's not approaching 0 any longer. Now it's approaching 1. The asymptote has moved up 1 also. To y equals 1 is the asymptote. If we put that line on there, it's approaching this line of y equals 1. It looks like it's touching it. But if we were to zoom way in on that, let's try to see how close we can get here. We'll eventually see that the red is not touching. Oh, see, it's not touching the purple. It's a 1.0004, where this is just 1. It just looks like, and it's just getting closer and closer as it goes down. The more we zoom in, the more we see that difference. But when we zoom back out where we were, it certainly looks like it's touching it. But it's not. So this k, if we did a minus, let's say minus 2 is our k. Well, look, instead of being at 4 for the y-intercept, now it's down at 0.2. And the asymptote, let's get rid of that. The asymptote, instead of being at y equals 0, is now at y equals -2. Now it's approaching -2. So this k is going to affect the y-intercept and the asymptote that the equation graph is approaching. Whatever that plus k is where the asymptote is going to move to. Plus 7. Now it's way up here at 7. And this jumped up instead of being at 4, because this one has a y-intercept to 4 because that's what our p is. Now it jumped up to 4 plus 7. It's up at 11. All right. So let's look at our notes for this thing. So let's talk about when P up here is positive. Okay, because we saw it do something different on that graph when we had a negative number for P. So when P is positive, all right, there are two situations. When the base is greater than 1, right? And when the base is, let me write this way, 0, between 0 and 1, right? Between 0 and 1. So when the base is greater than 1, or when it's a fraction, it's between 0 and 1. That's the two different cases we have here. So let's draw that. We'll draw a line across here. Okay. So the two different cases now. So when B is greater than 1, and here's our B. So when B is greater than 1, or when B is a fraction. If B is greater than 1, as was explained in that last video, when this is greater than 1, this is growth. This is increasing. Right? It's increasing. If this is 2, then it's doubling. If it's 3, then it's tripling. If it's 1.5, it's gaining 50%. Anytime it's bigger than 1, this is growth. Okay, growth. And we expect our graph then in that situation. We have a graph, right? And whatever k is going to be where our asymptote is. Let's say it's right there. That's y equals k. So we'd have a y equals k as our asymptote, and this graph would approach the asymptote on this end and increase. All right, that's what we would expect the graph to look like. Increasing graph, a growth graph, when P is positive and when B is greater than 1. All right, and K would be where the asymptote is. All right, good stuff there. So yeah, that would be the plus K. where the asymptote is. All right, now how about if b is not greater than 1? It's a fraction. It's between those. Then we see that as a decay. Decay. P is positive, but this is a fraction. It's decay. Well, what do you mean decay? Well, let's make P is positive with a 4. Let's take off the plus K for now. Let's just look at this one. If this is a fraction, let's say it's 0.5. See, this is decay. It's going down. It starts at a higher number, but as it moves on, x gets larger. It's decaying. It's going down. There's less and less left. It's going down and down and getting closer and closer to that asymptote at k, which is 0 in this case. So a decay function. So again, what we'd expect to see in our graph, which we just saw in the other graph there, again, whatever k is, it's going to determine the asymptote. Y equals k. And the graph is going to start high and then get closer and closer as it goes down. Again, the asymptote will be whatever k is. Okay, so that covers 2 of the 4 situations. The other situations happen down here when p is a negative number. When this number is negative to start the equation. So let's look at those situations. Again, this is great to have in your notes that you can use on any assignment, any quiz, any test. All right, again, b is greater than 1 or b is greater than 0 but less than 1. All right, so the 2 different cases for b. 2 different cases for b. So if b is greater than 1, it's still growth, right? Because we know anytime that's bigger than 1, as was explained with the boat example video, and when it's a fraction, it's decay. But what does the graph look like when p is negative? Well, draw our graph again. We'll again have this y equals k. We're going to be consistent with this y equals k. That will be our asymptote. But when p is negative, it starts close to the asymptote on this end and goes down. It's growing to be more negative, basically. If we're talking about that, it's growing to be more negative. Since p is negative, it's growing downward. That's going to be the way we expect to see our graph. So we're seeing basically a reflection of that, right? It's exactly like this, approaching the asymptote, but it reflects over the asymptote when you put in a minus in front of the whole equation. When the p becomes negative, it reflects downward. Over here with the fraction b between 0 and 1. Again, let's have that asymptote at y equals k. And in this situation, it will go from down here upward. Again, a reflection of this graph here, approaching the asymptote on the right side, the left side going to negative infinity or infinity when p is positive. So it's a reflection in that direction. So there's for your notes the 4 different ways that an exponential equation looks like. You'll always have one of these 4 types of graphs when you're graphing an exponential equation. It either starts close to the asymptote and goes up, or it starts up high at infinity and comes down to the asymptote, or it'll be below the asymptote, going down or going back up as we go left to right. All right. We'll switch back to our lesson there. Give you a second there in case you're writing that down in your notes. You can always go back to the video of this later when I get it posted and pull these off there, pause it when you need to. All right, let's go back to the lesson. Okay, so it talks about the end behavior and the y-intercept. So that's what we looked at in there. You know, the end behavior, it's either going down towards negative infinity or going up towards negative infinity. And the other end is going to be approaching the asymptote of whatever k is, y equals k. Here's the same thing that we just did. You can blow it up, make it look bigger. So if you're still working on your notes, you have this. But it gives the language for the end behavior. This is a growth function that starts at the line y equals k on the left and ends up on the right towards infinity. So this is if p is positive, and this is if p is negative. And there's the equation. We use pb to the x plus k as the base for this discussion. All right, so it says describe the y-intercept and end behavior of the following graph. So if we make that a little bigger, the y-intercept we can see is at 0, -1. Okay, it crosses the y-axis at -1. And the end behavior, the left end goes up towards infinity. The right end approaches the asymptote of y equals -2. You see it's approaching -2. That's the end behavior. Left goes up towards infinity. Right approaches the asymptote of -2. Let's see what they say. Y-intercept is 0, -1. The graph starts up on the left and decays downward close to -2 on the right. So basically, if you said something similar to that when asked to describe the end behavior, you'd be in good shape. All right, average rate of change. Let's talk about average rate of change. And let's, well, we don't need Juan's example. We can do our own right here. Let's do this one. This would be a type of problem you would see on a test or on an assignment. And we're going to do this on paper so we can go through this. You can go up and read about Juan's example if you want. But it would be asking for the average rate of change. What's another word for that? You've heard average rate of change ever since you've been in algebra. I'm writing this equation down. If anyone knows what the average rate of change, what's another word for that? Put it in the chat. I just want to know if you know. Do you know what another word is for average rate of change? All right. I'm going to switch over here. Oh, and they want to know from x equals 1 to x equals 3. Nobody knows average rate of change. I was just looking at the chat. Average rate of change. What's another word for that? I'll give it to you. It's the slope. What's the slope? That's the average rate of change. How much does it change from here to here? That would be the slope. We're going to look at that on paper here. All right. So they want to know the average rate of change. Slope. The slope for this equation from x equals 1 to x equals 3. And like, oh, well, we could graph it and look at it that way. Okay, let's try that. Let's get rid of these. F of x or y, you put y equals 3 times 4 to the x power. Okay, there is the equation graphed. When x equals 1, well, where is it when x equals 1? Oh, I don't like how it's showing the minor axis. Just show me the ones. Okay. Okay, so when x equals 1, it's way up here. Oh, it's 12. 112 is there. And then we'll say when x equals 3. Well, x equals 3 way up here somewhere. Wow, we got to find the slope between here. Ooh, wow, 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 wow. When I graphed it, I found, let's see, where is it? Somewhere close. Oh, it's higher than that. I'm not up there yet. There it is. 3,192. Wow. Okay, 3,192. So it's way up there. And we're trying to find the slope between those points. Now look at the graph. It's like, I have no idea what the slope is. No, it doesn't. So if we want to find the slope, there's a slope formula that you learned way back in Algebra 1. You take the y value of the second point and subtract the y value of the first point and divide that by the x values subtracted from each other. So the first point would be 1 something, and the second point would be 3 something. I know we looked at it in the graph, but we're going to figure out how to do it algebraically. Oh, this is not 4 to the fourth. It's 4 to the x. 4 to the fourth is not an exponential equation. The x has to be the exponent. Okay, so when x equals 1, when x equals 1, instead of x, it's 1. So instead of x, it's 1. All right, instead of x is 1. 4 to the first power. Well, that's just 4. So this is just 3 times 4, which is 12. So there's our first point, 112. When the x is 1, the y is 12. When x is 1, the function equals 12. Y equals, or f of x equals. How about when it's 3? Okay, so when f is 3, now it's 3 times 4 to the third power, which means it's 3 times what? 4 to the third power. Well, you probably know that in your head, hopefully. But we'll go ahead and do it in the calculator just so everybody can see that and not get the mess. So there's 4 to the first power. When I multiply it by 4, that's 4 squared. When I multiply that times 4, that's 4 to the third power. So it's 64. And hopefully you know that in your head, 3 times 64. But if you don't, times 3, 192. Okay, let's get rid of the calculator. So when x is 3, the equation equals 192. So there's our 2 points. And it's asking for the average rate of change between those 2 points from x equals 1 to x equals 3. Well, let's use this formula. If you don't have that memorized, that's good for your notes as well. I'll highlight that. So slope, remember m is slope. Oh, slope, average rate of change, slope, m equals y2. What's the second one? 192. Minus y1. What's the first y? What's the second x? 3. What's the first one? 1. 192 minus 12. Well, we can see that's 180. Divided by 3 minus 1 is 2. So the average rate of change is 90. That's our answer. That's the average rate of change between those 2 points. So that means if that's the average, when we go up from 1 to 2, we would just add 90. Because that's what it averages between these 2 points. So the 2 would be 2102. And then we add another 90, that gets us to 192. That's if you draw a straight line from x equals 1 to x equals 3, from this point to this point. Now we know when we graph that, that's not a straight line. It's slowly getting steeper as it goes. But we're talking about the average. On average, just drawing a straight line, on average, it goes up 90 every time between 1 and 3. It goes from not 12 to 102 to 192. Now, some of you may say, what if I get this backwards? Because I don't know which y2 and y1. Well, you get a pick, which is one y2 and y1 out of those 2 points. But what if you did do it the other way? Okay. M equals, let's say we did this backwards. And we said, okay, this is 12 minus 192 and 1 minus 3. Well, that's okay. The only thing that would mess you up is if you did y2 and x1. As long as you do the same x and y's, if you said this is x2, y2, well, make sure those numbers are both first. If you said those are x1, y1, make sure they're second, and then these will both be first. Doesn't matter as long as you're consistent. 112 minus 192. Well, that would be a negative 180 because 12 minus 192, we subtracted a bunch, that's negative 180. And 1 minus 3 is negative 2. Well, look, negative 180 divided by negative 2, your answer is still 90 because negative divided by negative is positive. So it doesn't matter which point is y1 and x1 and which point is x2, y2. Your choice. Your choice. So either way, you should get the right answer. But that is the average rate of change or the slope between 2 points. Between 2 points. Use the slope formula. Slope formula. All right. Let's go back to here. So they went step one. Step one is finding what the 2 points are, 112 and 392. That's what we did. Step two is using the formula. 192 minus 12, 3 minus 1, 180 by 2. The average rate of change is 90. So there you go. If you want an example for your notes, there's a nice example. I did it on paper, or they did it very cleanly here on page 2, and you can put that in your notes. All right, let's look at page 3. All right, so to this point, we've only used f of x equals bx, or b is the base. So here they want to play with it. Now, let's write down what formula they're playing with here, because what they're doing is they're showing the translations. We've already played a little bit of translations on Desmos, but let's do it the way they're showing. So they're saying, okay, if you have the equation f of x equal, and this time they're using a instead of p base, and they're doing x minus, I'm going to put h, I'm not sure what number they use, plus k. A, B, H, and K. Is that what they use? Okay, that's what they used. All right, so the most basic form of this would just be b to the x, right? That's if the a was 1 and h and k were both 0. Now, if you remember before, we've used h and k before for translations. K moves it up or down. When we put a number on the end, it's going to move it up or down. And we already looked at that on Desmos a few minutes ago when we were playing with this. Let's zoom back in here real good. When we added a +2, the graph moved up +2. The asymptote moved up, the y-intercept moved. When we made it a -2, it moved down. Asymptote and everything. If there is k is 0, it doesn't exist. It's just a normal graph. But what about this h it's talking about? And we did look at the a, the number they put out in front of this a. That affects how steep it is, right? If this is just 1, it's that steep. But if it's 10, it's that steep. See how much steeper it got? If it's 5, if it's 4, it's 3, it's 2. That just tells how steep it is. That's what the a does. A steepness. And by the same token, if a is a fraction, it'll be even less steep. Look at it. If we make a 0.2, which is 2/10, see, it's even less steep now. Now it's way over here. 0.1, 0.05. See, it just changes that. Go back to a 2. It's steeper. But the only thing we haven't looked at is this minus h. Just like before, so k is up and down, a is steepness, h, just like it did with quadratics and third power, is left and right. H moves it left and right. Let's play with that on Desmos. Okay, so they're doing, let's just say we got 4 to the power of x minus h. And we're going to add a slider. So when h is 0, that's when we just have our normal equation because we're not subtracting anything. It's just x. But how about when x is 1 or 2 or 3? Look, the larger h is, the more it moves right. If x is a negative, if h is a negative number, it moves left. Now notice we're subtracting h. So in order to move left way over here, h would have to be -4. I'll just take off the slider. X minus -4, which we also see as x plus 4. That's the same thing. It didn't change the graph at all. When I change that from minus a negative there to just say, no, let's just call that a plus. That's the same thing. So if you see x plus 4, it moved left 4, because here was the original equation. Y equals 4 to the x. See, instead of being over here at 0, 1, now it's at -4, 1. It moved left 4. This point here that was at 1, 4 is now over here at -3, 4. There it is, -3, 4. Just move left. If this is -4, it moves right. See, instead of 0, 1, now it's at 4, 1. Well, if I get it right there. There it is, 4, 1. So x minus h is going to move things left and right. And remember, it's just the opposite. If h is positive, then it's going to move left. If h is negative, it moves right. So that's how that affects translations of the graph. So they show that right here. If we have, let's see, vertical. Oh, they need a base that's different though. Okay. As we change the k, plus or minus, it goes up and down. As we change the h to a positive, oh, that's, yeah. It moves it left and right. Left and right. So that's what the h does, moves it left and right. And then it gives you some examples if you want to see some more examples of that. It says graph this using graphing technology, which you can do. You can go to Desmos and type in that equation. And then, is this a reflection of this? This is a reflection. Check it out. So you can look at those 4 examples. Page 4. Fitting functions to data. Here's the other thing we need to talk about. Sometimes we got data and we're trying to figure out the equation. So here's some data that's been collected. Here's the x, here's the y. This is a table. -5, -1, -2, -1, 0, -2, 1, negative. So it says, okay, let's try to find an equation to match this with this a, b, h, and k. So let's take these points, -5, -1. So -5, -1, -2, -1, -2, -1, 0, -2. It should be fun. You can play with this on your buzz. 1, -3. And 2, -5. All right, and now we want to find an equation that would match that. So let's see, the a has to be at least a 1 to have an equation. We have to have a base that's bigger than 0. Well, actually, I guess the a would have to be negative, right? We have to have a negative number out front. Let's go -1. Oh, okay, now we've got something getting closer. I put a base of 2. Let's do a k of -1, right? Because we need to move this down 1. Oh, that's really close. This actually goes through 4 of our points. And our equation is -1 times 2 to the x minus 1. Because we made h 0. We didn't do anything with h. We didn't move it left or right. We didn't need to. But this is what's called an equation of best fit. Because it's not exact, because there's no way we can get exact, because this goes straight. Those are both the same y, -1. So this would have to be flat and then curve. So this is the equation of best fit. Now, I will tell you there's more than one answer here, because look, when we check our work, we said -1, 2, 0, -1. They did the same thing with 2, -2, -1, and -1. And they got the exact same graph. But they have different numbers. They chose different numbers than we did and got the same graph. So there's more than one way to find that equation for the line of best fit. All right, page 5. I think this is our lesson summary right down here. Yeah, lesson summary. You can read this example. It's talking about combining two functions together, because you can do the same thing with these that we did with linear and quadratic, is you can multiply them together, combine them. But let's look at this lesson summary. Graphing exponential functions. That's what we're focused on this time. You can do it in Desmos. You can do it on a calculator if you have a graphing calculator. But make sure you can graph that. Here is 3 to the power of x. That's the exponential equation. We talked about the key features, the y-intercept, the end behavior, and finding the average rate of change. And then we did this. A function is said to be a best fit if it passes closest to the given data points. It may not go through all the data points, but it should be the closest one you can find close to that. And we can add functions together. We can subtract functions. We can multiply functions. Okay, let's look at the assignment that goes with this. There's several pages of examples there if you need more practice. Okay, this says which graph models the function f of x equals -4 times 2 to the x. What did we learn about that -4, that number out front? That's usually the y-intercept, unless there's a plus k, right? Or if there's an h. If there's an h or k, that can translate it left or right or up and down. But this doesn't have that. That just has -4 times 2 to the x. So we know it should have a y-intercept. We can throw it out, because that one's not -4. This one has a -4. This one has a -4. This one does. So it's one of these two. So one thing you can do if you're trying to figure that out, this is a -p and a base greater than 1. You can go back to your notes and go, oh, if I have a -p and a base greater than 1, my graph should look like this. Which one of those graphs look like that? None of them actually, does it? -p. Maybe you should graph that on Desmos and see why that's different. 2 to the x. All right. Let's go down here to number 2. Given this function, which shows the exact same function, but has a k of -1. If you took 2 to the x -1, which one of these would be the graph of that? Here, a boat's value over time has this function, 400 b to the x plus 0. If the boat increases 25% per year, which graph would it be? So that would change the base. It has to be greater than 1. He did that in his example of a boat increasing in value. So which one of those 4 graphs? And this one just says you describe the y-intercept and the end behavior. Here's your 4 choices. Which one of those describes the y-intercept and end behavior? And then this one, estimate. Oh, I love this. This is basically, can you read a graph? The revenue each season from the tickets at a theme park is represented by T of x equals 5x. The cost to pay the employees is represented by 1.5x. So here is a graph of the combined function. So this takes both of those into account. It adds them together. And it wants to know, what is the profit after 4 seasons? So here's number of seasons. Can you read the graph and tell me after 4 seasons, what is the profit? You don't even need to know these equations because they already graphed it. All you have to do is, can you read a graph? which is real important in the business world. In the business world, you'll get graphs and data all the time, and you got to be able to look at a graph and know, what is this graph telling me? So for this theme park, after 4 seasons, what is the profit? 1, 5, 10, or 15? All right. Let's look at our next lesson, which is much shorter, which is good because we've been here an hour. We don't have another hour. Graphing log functions. How do you grab logarithmic functions? So remember, a graph is a reflection of its equivalent exponential equation. Like log 10 to the x is the same as y equals log of x, base 10, and those are reflections of each other over that line y equals x. Y equals x. Just like 2 to the x and log base 2 to the x are reflections of each other over that y equals to the x. So let's look at what do we know about logarithms. It says graph this using graphing technology. So log x minus 3. So let's do that. F of x equals log parentheses x minus 3. There it is. That's base 10, obviously, because we didn't put a base. So it's base 10. This is base 10. Notice it goes through the x-intercept at 4. And this has an up and down asymptote. Logarithms have up and down asymptotes. An asymptote at x equals 3. Notice it gets closer and closer and closer to this 3, but it never touches it. Logarithms have an x equals asymptote. Exponential has a y equals asymptote. Up and down versus vertical. So this shifts, this minus 3 shifted that to the right, 3. If we just did log of x, there's the normal equation. It's going to cross through 1, 0 and never touch the y-axis. But if we do minus 3, that's a shift, right? That's a minus h. It moves it over to the right. So the vertical asymptote becomes x equals 3 instead of equals 0 because of that minus 3. See, then they show both of them there. All right, so here's the part. Notice we have the lesson summary already on page 2. This is a very, very short lesson. Maybe you noticed by now that logarithms get really close to the y-axis, like really close, but they never cross the y-axis. See that? It never, if we go down in here and zoom in, it is not going to be on the y-axis. It's going to be really close, and we're going to have to zoom in a long ways to see that. But we're still zooming, still zooming. It still looks like it's on the y-axis. See what it say the value is. I can't even click the value of it. Oh, wait, we got there. Oh, look, it's not even close to the y-axis when we zoom really, really far in. But as we zoom out, now it starts to look like it's on the y-axis again. But it doesn't. It doesn't touch the y-axis. And if you zoom in enough, you see that. Hi, Emery. All right. But the only way, look here, the only way to make a logarithmic function cross the y-axis and have a y-intercept is to give the function a horizontal shift. We gave it a horizontal shift to the right by being minus 3. What if we made that a plus 3? Oh, now look, it has a y-intercept. I'm emphasizing this because this is very important for your assignment. The assignment for this lesson is not multiple choice. This is something you have to do on paper. And this is a third of the grade right here, knowing how to get a y-intercept. You have to shift horizontally. If I take that shift off, I put plus 0. There's no shift. It does not have a y-intercept. If I shift it over, now I have a y-intercept. So hopefully you paid attention to that. A horizontal shift is the only way to have a y-intercept. If the parent function is log 10 of x, a transformation of x plus 2 will result in it being shifted 2 units to the left across the y-axis and will make a y-intercept occur. Okay, lesson summary. Took us 5 minutes to do this lesson. A logarithmic function is the inverse of an exponential function, and you'll see it as a reflection. All right, it will have a vertical asymptote instead of a horizontal asymptote. And if you put a plus something with the x, that's a horizontal shift. Right? If you put plus 6 outside the x, not with that, that's a vertical shift. That's up and down. Right? If we do x plus 2, see, that one went up and down because it's not in the parentheses with the x. This one is in the parentheses with the x, and that shifted it left. That's the green one. Okay, let's look at our assignment. Oh, wait, look here. There's no assignment, no questions on the assignment page. Submit the complete assignment following the instructions in the lesson. Let's go back to the lesson, to the last page. The last page of the lesson. Page 4. And there you go. Assignment. It's down at the bottom. Scroll down. 2 options, work alone or work collaboratively. I could pair you up in groups if you want me to, put you in partners, but most people prefer not to. We're going to do work alone. All right, here's the assignment. Now let me show you, if you go to Google Classroom, this will be the easiest thing to do. Go to Google Classroom, go to the classwork tab, go to week 22, do this weekend buzz, click on that. And here's a template for you to use for this assignment. Click on this. Here is your assignment. 1, 2, 3. I got them numbered right here. Here's the 3 things you have to do. 1, 2, and 3. First, you have this. Have you ever been in a swimming pool and your eyes were red when you got out? That means the chemicals in the pool were not adjusted correctly. More specifically, the measurement of the pool's pH was not quite right. pH is the measurement of the hydronium ions. It can be modeled by this function. I put the function in bold to make it stand out. F of x equals negative log 10 of x. You can put that in Desmos, negative log 10 of x. You don't have to put the 10. If it's base 10, right? If I just want to do that, f of x equals negative log x. That is negative log 10 of x, because if you don't put a base, it assumes base 10. So look, I've already made the graph. X represents the hydronium atoms. F of x gives the pH. So different liquids have ideal pH values. Water at 25 degrees Celsius is a pH of 7. That's neutral. 7 is neutral. Anything that has a pH less than 7 is acidic. If it's above 7, it's basic, which is, cancels out acid. Alkaline, also known. Seawater has a pH of more than 8, so it is not acid, it's the total opposite. Where lemonade has a pH of 3, there's a lot of acid in lemonade. So here's your assignment. First, create a graph of the pH function, either by hand or using Desmos or a calculator. I've already did that just a second ago. If you were watching, I went to Desmos and created the graph of that function right there. All right, locate on your graph where the pH value is 0 and where it is 1. So that's what you need to answer on this. You can take a screenshot and paste your graph in here and then answer this question. Where is the pH value 0 and where is it 1? Which means what's the x that makes it 0 and 1. Number 2, use your graph to find what is the pH level if the hydronium ions is 0.5. So what's the pH? Look at the graph. Give that answer. What is the pH level if x equals 0.5? Then your third problem, the pool company developed new chemicals that transform the pH scale. Using the pH function, here's the same function. Notice that's the same one. Explain below which transformation results in a y-intercept and why. Do you put a +1 at the end of the equation, or put a +1 in the parentheses with the x. Which one of those, and I just emphasized that for like 2 or 3 minutes. That was most of what I emphasized. Which one of those results in a y-intercept? Because we said that a log function does not have a y-intercept because it has a horizontal asymptote at y equals 0. X equals 0. X equals 0. But a transformation can make it have a y-intercept. Which one? Which one? If you want, you can graph showing the transformations. That's optional. You don't have to include a graph of the transformation. But if you do, be sure and tell me what transformation the graph is of, so I know what you graphed. But you just need to explain which one of those does it. So that's it. 3 questions. That's your assignment. You can use this template. When you click on this template, it'll create a copy of it in your Google Drive. So then when you go back to Buzz and you go there, you just choose the file. Choose the Google file, attach it, and submit it. That's it. That is it. So you have a multiple choice assignment on 5.05. You have an assignment with a template in Google Classroom for 5.06, graphing logarithms. Then we'll be done with exponential logarithms. Next week, we'll test over it and move on to something else. So, all right, guys, that's all I got for you. You got enough time to start your grade check if you want. We're doing grade checks this week in your advisory class. I did update all the grades this morning, so your grade in Hack should be accurate. The grade in Buzz is always the most accurate, but I've transferred those grades in Hack, so it'll be there when you're looking up all your other grades as well. So, all right, this is a B-Day Friday, but I am not here Friday, so we will have class Thursday, and then I'll be out on Friday. So I will be here Thursday if you need to be here, or if you want to be here. Either way, but it's not mandatory unless your grade's below 70. So, see you.